Hey everyone, and welcome to another deep dive.
Happy to be here.
This time we're tackling some physics, exploring excerpts from a university textbook that a listener shared with us.
It's always fun to break down these complex ideas and pull out those golden nuggets of knowledge.
Exactly. Our mission is to make this dense material accessible and maybe even, dare I say, enjoyable.
We'll be covering a lot of ground, from the experimental nature of physics and the importance of models, to the nitty-gritty of units, prefixes, and even those sometimes confusing vectors.
But don't worry, we'll guide you through it all step by step.
By the end of this deep dive, you'll have a solid foundation for understanding some of the most fundamental principles of physics.
Sounds good to me. Now, one thing that jumped out at me right away in these excerpts is how physics is presented as this incredible adventure of discovery. It's not just about labs and equations, it's about exploring the mysteries of the universe, from the smallest particles to the largest galaxies. Absolutely. The textbook emphasizes how physics is interwoven with so many different fields, from paleontology to climatology. It's like a universal language that helps us understand how things work at a fundamental level.
So it's like physics is the ultimate detective, helping us solve mysteries across the universe. And it's not just about these big, abstract concepts either. It explains everyday things too, right?
Definitely. It's all connected. Physics helps us understand why the sky is blue, how satellites stay in orbit, and even how our smartphones work.
Now, speaking of understanding, the textbook dives into something called physical theories. And to be honest, I always found that term a bit intimidating.
I get that. It sounds very formal, almost like a set of rules carved in stone.
Right, like unbreakable laws governing the universe.
While it's true that physical theories are based on rigorous observations and experiments, they're not set in stone. They can evolve and change as new evidence emerges.
So you're saying even those fundamental laws of physics are open to revision? That's pretty mind-blowing. Does that mean everything we know could be overturned one day?
It's less about overturning and more about refining our understanding. Think of it like building a house. You start with a foundation, and as you learn more, you add new floors and remodel certain sections. But the core structure often remains the same.
Okay, that makes me feel better, knowing that science is constantly evolving but also builds on what we've already learned. But let's be honest, a lot of us hit a wall when it comes to actually solving physics problems. I remember struggling with those back in school. I could understand the concepts, but putting them into practice, well, that was a different story.
I think we've all been there. The textbook acknowledges this common challenge and emphasizes that problem solving is where our understanding is truly tested. Is where the rubber meets the road, so to speak.
So how do we bridge that gap between knowing the concepts and actually being able to solve problems?
The textbook offers a really practical framework called IC. It stands for Identify, Set Up, Execute, and Evaluate.
I see. I love it. It's catchy and makes it seem much less daunting. Can you break down each step for us?
Sure. So first, you identify the relevant physics concepts involved. What principles are at play? What formulas might be useful? Then you set up the problem. Define your variables, draw a diagram, and make sure you understand what's being asked. Next, you execute the solution using the appropriate equations and mathematical tools. And finally, you evaluate your answer. Does it make sense? Are the units consistent? Did you answer the question that was asked?
It sounds like a more organized and logical approach than I remember from my school days. I wish I had known about IC back then.
It's never too late to learn new tricks. And this framework can be applied to a wide range of physics problems, making them much more approachable.
Now here's where things get a bit more abstract. The textbook talks about idealized models, and that always makes me wonder, how can a model be idealized? Is physics getting into abstract art now?
Not quite abstract art, but it is a fascinating concept. Idealized models are simplified representations of complex systems. They help us make problems more manageable while still capturing the essential features.
I see. So it's like creating a map. We don't need to show every single tree and house, just the main roads and landmarks to help us navigate.
Exactly. But we need to keep in mind that models, like maps, have limitations. Their accuracy depends on the assumptions built into them.
So if those assumptions don't hold up in the real world, the model's predictions could be off.
That's right. It's like using a road map to navigate a city that's under construction. The map might not reflect the latest changes, leading you astray.
That makes sense. It highlights the importance of choosing the right model for a specific situation. Okay, let's shift gears and talk about something that can be a real headache, at least for me. Units of measurement. It feels like there are endless ways to measure the same thing.
It can definitely be a bit overwhelming, especially when you're dealing with different systems of units.
I still have nightmares about trying to convert between metric and imperial units back in high school. Like how many ounces are in a liter? Who knows?
Well, the textbook dives into this topic, explaining that to avoid confusion and ensure consistency, scientists rely on the International System of Units, commonly known as the SI system, or the metric system.
Ah, yes. Meters, grams, and liters, right?
You got it. It's a logical and widely used system that provides a standardized way to express measurements. It's like having a universal language for science and engineering.
And sometimes we need to convert between different units, like converting miles per hour to meters per second, right?
Exactly. The textbook even gives the example of the thrust SSC, that supersonic car that broke the sound barrier. To grasp the sheer speed of that car, they converted its speed from miles per hour to meters per second.
It's like translating a book from one language to another so that everyone can understand the story, regardless of where they're from.
That's a great analogy. Unit conversion is all about making sure we're all on the same page when it comes to understanding measurements.
Okay, now let's break down the building blocks of the SI system. Those fundamental units that form the foundation of so much of physics.
We're talking about time, length, and mass. They're like the primary colors of the physics world, so to speak.
And each of those units has its own special way of being defined, right? It's not just some arbitrary ruler or clock.
Exactly. Time is measured in seconds, and a second is defined by the vibrations of a cesium atom in an atomic clock. Length is measured in meters, and a meter is defined by the distance light travels in a tiny fraction of a second. And mass is measured in kilograms, which is now based on Planck's constant, a fundamental constant in nature.
Wow, I never realized there was so much science packed into those seemingly simple units. It's amazing how precise those definitions are, ensuring consistency across the globe.
It highlights the rigor and attention to detail that underpins scientific measurement. And to make things even more convenient, the metric system uses prefixes to create larger and smaller units.
So we don't have to write out really long numbers with lots of zeros.
Exactly. We can use prefixes like kilo, centi, and milli to simplify our expressions.
So a kilometer is 1,000 meters, a centimeter is 1/1100th of a meter, and a milligram is 11,000th of a gram. Okay, it's all coming back to me now.
Excellent. These prefixes are essential for expressing measurements efficiently and accurately. Now, the textbook also emphasizes another important concept, dimensional consistency.
Ah, yes. Dimensional analysis. I remember struggling with that too.
It's a crucial concept for making sure our equations and calculations make sense. Basically, it means that the units on both sides of an equation must match. You can't add apples and oranges or meters and seconds for that matter. Units are treated just like algebraic symbols.
So it's like a built-in error checking system for physics problems. If the units don't add up, you know you've messed up somewhere.
That's a great way to think about it. Dimensional analysis helps us catch errors and ensures our results are physically meaningful. It's like making sure you're comparing apples to apples.
Okay, that makes sense. It's like a sanity check for our calculations. Now, speaking of errors, the textbook also mentions that all measurements have uncertainties, which makes sense, right? No measurement can be perfectly precise.
Exactly. There's always some degree of uncertainty or error associated with any measurement. It depends on the instrument used, the measurement technique, and even environmental factors.
Right. So those digits after the decimal point aren't just there for decoration. They tell us something important about the precision of the measurement.
Exactly. Significant figures help us convey the precision of a measurement. The more significant figures, the more precise the measurement.
So it's not just about getting the right answer, it's about understanding how confident we are in that answer.
That's right. And here's where it gets a bit tricky. Uncertainty propagates through calculations. We need to consider how those uncertainties carry over into our final results.
So it's not just about plugging numbers into a calculator and blindly trusting the answer.
Exactly. We need to be mindful of the limitations of our measurements and how those limitations affect the accuracy of our calculations.
Okay, I'm starting to see how understanding uncertainty is crucial for interpreting scientific data and drawing meaningful conclusions. We can't just ignore those error bars. Now, remember those really large or small numbers we talked about earlier, like the distance to a star or the size of an atom? There's a special way scientists handle those, right?
You're talking about scientific notation.
Yes. It's like a shorthand way to express those mind-bogglingly large or tiny numbers.
It's all about expressing a number as a value between 1 and 10, multiplied by a power of 10. For example, the Earth's mass, which is about 5,970 billion kilograms, becomes 5.97 by 10 to the power of 24 kilograms in scientific notation.
Wow, that's much easier to write, and it prevents a lot of potential errors from counting all those zeros. But wait, didn't we say there are two important factors in a good measurement? Precision and...
Accuracy. Precision and accuracy are often used interchangeably, but they have distinct meanings in science. Precision refers to the level of detail in a measurement, while accuracy refers to how close a measurement is to the true value.
So a measurement can be precise but not accurate, or accurate but not precise.
Exactly. Imagine a dartboard. If you throw 3 darts and they all land very close together, that's high precision.
Yeah.
But if they're all far from the bullseye, that's low accuracy.
Ah, okay. So precision is about consistency, while accuracy is about hitting the target.
That's a great way to put it. And in science, we strive for both precision and accuracy to ensure our results are reliable and meaningful.
Now, before we move on to the fascinating world of vectors, let's talk about a technique that sounds more like something you do on the back of a napkin than in a physics lab: order of magnitude estimations.
It sounds informal, but it's a surprisingly powerful tool. Order of magnitude estimations are rough approximations used when we don't have precise data or when a calculation is too complex to perform accurately. The goal is to get a general sense of the scale of a phenomenon.
So it's like a quick and dirty calculation to see if we're in the right ballpark.
Exactly. The textbook gives the example of estimating the weight of a suitcase filled with $1 billion in gold.
Right. It showed that even a rough calculation can lead to surprising and insightful results.
It helps us grasp the scale of a problem and can even be used to check the reasonableness of more precise calculations.
Okay, that makes sense. Now, are you ready to tackle those mysterious entities known as vectors?
Absolutely. Vectors are essential for describing many physical quantities, especially those related to motion and forces. They're like arrows pointing us in the right direction, both literally and figuratively.
Okay, here we go. I'm ready to unravel the mysteries of vectors. But first, can you remind me again what makes a vector different from a scalar? I always get those terms mixed up.
No problem. It's an important distinction. Scalars are quantities that are fully described by a single number, their magnitude. Think of things like temperature, mass, or time.
Okay, so a scalar is just a number with a unit, like 25 degrees Celsius or 5 kilograms.
Exactly. Vectors, on the other hand, need both a magnitude and a direction to be fully described. Think of quantities like velocity, force, or displacement.
So it's not just about how much, but also which way.
Precisely. If I tell you I walk 3 kilometers, that doesn't tell you the whole story. I need to specify whether I walk north, south, east, or west for you to know where I ended up. Displacement, which is the change in position, is a prime example of a vector.
So when we talk about displacement, it's not just about the distance traveled, but about the net change in position, like taking a shortcut through space-time.
I like that analogy. Now, how do we visually represent these vectors with both magnitude and direction?
I remember from the textbook that we use arrows, right?
That's right. The length of the arrow represents the magnitude of the vector, and the arrowhead indicates the direction. It's a simple but powerful way to visualize vectors.
So a longer arrow means a larger magnitude, and the direction the arrow points tells us which way the vector is acting.
Precisely. And remember, displacement is always a straight line, from the starting point to the ending point, even if the path taken was curved.
So even if I wander around aimlessly, my displacement is just a straight line from where I started to where I ended up.
That's fascinating. But what about those situations where we need to combine multiple vectors, like if I walk east for a while and then turn north? How do we deal with that?
That's where vector addition comes in. Adding vectors isn't as simple as adding regular numbers. We need to consider both their magnitude and their direction.
Right, because walking 3 kilometers east and then 3 kilometers north doesn't land you 6 kilometers from where you started.
Exactly. One way to visualize vector addition is the head-to-tail method. We draw the first vector, then draw the second vector, starting from the head of the first vector. The vector sum, or resultant vector, is the vector drawn from the tail of the first vector to the head of the second vector.
So it's like following a treasure map. Walk 3 paces north, then 4 paces east, and the resultant vector leads you straight to the buried treasure. That's a perfect analogy. And remember, vector addition is commutative, meaning the order in which you add the vectors doesn't matter. You'll end up at the same spot whether you go east then north or north then east.
So no matter which path I take on my treasure hunt, the treasure will always be in the same spot. That's reassuring.
Exactly. But what if, instead of adding a vector, we want to subtract it?
That's interesting. I hadn't thought about vector subtraction. What does that even mean?
Subtracting a vector is the same as adding its negative. The negative of a vector has the same magnitude but points in the opposite direction.
So if I walk 3 paces east and then want to undo that movement, I'd need to walk 3 paces west, right?
Precisely. You're essentially adding a vector that cancels out the effect of the original vector. You can visualize vector subtraction by drawing the vectors head-to-head, and the vector difference is the vector drawn from the tail of the first vector to the tail of the second vector.
It's like taking a detour, but ultimately still ending up back at our intended destination.
In a way, yes. You're accounting for a change in direction, and the vector difference represents the net effect of that change.
Okay, so we've covered adding and subtracting vectors. But what about those cases where vectors aren't neatly aligned with our coordinate axes? Like those diagonal vectors that go off in some random direction. How do we handle those?
That's where components come into play. They're a powerful tool for working with vectors of any orientation.
I remember the textbook briefly mentioning components. It's about breaking down a vector into its projections along the x and y axes, right? Like if you shine a light on it from the side and look at the shadows it casts.
That's a great visual. By resolving a vector into its x and y components, we can work with them separately and then combine those results to find the overall effect.
So we're essentially taking that diagonal vector and turning it into two perpendicular vectors that are easier to work with.
Exactly. It simplifies vector calculations, especially when we're dealing with multiple vectors at various angles. Components allow us to treat those diagonal vectors as a combination of horizontal and vertical movements.
Okay, I'm starting to see how components can be helpful, but didn't the textbook say there are 2 ways to multiply vectors? What's that all about? I thought multiplication was just multiplication.
Well, with vectors, things are a bit more nuanced. We have the scalar product and the vector product, both with unique applications in physics.
2 different ways to multiply vectors. Okay, my brain is starting to hurt. Can we take it one step at a time? What does the scalar product tell us about two vectors?
The scalar product, also known as the dot product, gives you a scalar quantity, a single number. It's a way to measure how much two vectors agree with each other in terms of their direction. It's like shining a light on one vector and seeing how long its shadow is on the other vector.
Okay, so the more the vectors align, the longer the shadow and the larger the scalar product.
Exactly. The scalar product is maximized when the vectors are parallel, meaning they point in the same direction. And if the vectors are perpendicular, their shadows don't overlap at all, so the scalar product is 0. It's like they're completely ignoring each other.
So it's like a measure of how much two vectors are working together.
That's a good way to think about it. Now, the vector product, or cross product, is a bit more complex. It gives us another vector as the result, and this new vector is perpendicular to both of the original vectors.
Wait, a new vector. Okay, I'm going to need a diagram for this one.
Imagine 2 arrows lying flat on a table. The vector product gives you a third arrow that's pointing either straight up from the table or straight down.
Whoa, we're going 3D now, so we're not just talking about the length of the vectors anymore. We're also considering their orientation in space.
Precisely. And this new vector's magnitude represents the area of the parallelogram formed by the 2 original vectors. It's like a visual representation of how much those 2 vectors span a certain space.
Okay, so the vector product gives us a new vector perpendicular to the original 2, and its magnitude is related to the area they enclose. But how do we know if that new vector is pointing up or down?
That's where the right-hand rule comes in. It's a handy trick for visualizing the direction of the vector product. Point your right-hand fingers in the direction of the first vector, and then curl your fingers toward the second vector. Your thumb will then point in the direction of the vector product.
Okay, I'm definitely going to need to practice that one in the mirror.
It might feel awkward at first, but it's a helpful visualization tool. Now, one key difference between the scalar product and the vector product is that the scalar product is commutative.
Meaning the order of the vectors doesn't matter, but what about the vector product?
For the vector product, the order does matter. It's anti-commutative, meaning if you switch the order of the vectors, the direction of the resulting vector flips. So AB does not equal BA in this case.
Okay, so we need to pay attention to which vector comes first when we're calculating the vector product, but not for the scalar product.
Got it. And we saw that the scalar product is at its maximum when the vectors are aligned, while the vector product is at its maximum when they are perpendicular. That seems counterintuitive. It does seem counterintuitive at first, but it all boils down to what each product is measuring. The scalar product is about agreement, while the vector product is about the interplay of their directions and the space they enclose.
Okay, I think my brain needs a break after all that vector talk. We've covered a lot of ground in this first part of our deep dive. We've explored the nature of physics, the role of models, and the intricacies of units, uncertainties, and significant figures. And we've even started to dip our toes into the fascinating world of vectors with their magnitudes, directions, and various ways of combining them. It feels like we're building a solid foundation for understanding more complex physical concepts.
You're absolutely right. We've laid the groundwork, and in the next part of our deep dive, we'll delve deeper into some of the more advanced concepts and applications of vectors, seeing how they play a crucial role in describing motion, forces, and other fundamental principles of physics.
I'm already intrigued. I can't wait to explore further. See you in part 2.
Looking forward to it.
Welcome back, everyone, for part 2 of our physics deep dive.
Glad to have you back.
We're picking up where we left off, exploring those intriguing entities known as vectors.
They're key players in the world of physics.
And in the last part, we talked about how we can use components to simplify vector calculations, especially when dealing with vectors that point in all sorts of directions.
Components are like breaking down a complex problem into smaller, more manageable pieces.
It's like having a set of instructions telling us how much to move in the x direction and how much to move in the a direction to reach a destination.
Precisely. Instead of dealing with that diagonal vector directly, we can just focus on its horizontal and vertical contributions.
And once we have those components, we can use the Pythagorean theorem and some trigonometry to calculate the overall magnitude and direction of the vector.
It's like piecing together a puzzle, starting with those individual components to reveal the complete picture.
I'm definitely starting to see the power of components in simplifying vector calculations. Now, I want to revisit those two ways of multiplying vectors. I'm still trying to wrap my head around the difference between the scalar product and the vector product.
It's easy to get them mixed up at first, but they really represent two distinct operations with different applications.
Okay, so remind me again. The scalar product, also called the dot product, gives us a scalar, a single number, and the vector product, or cross product, gives us another vector.
You got it. But it's not just about the type of result we get. It's about what those results tell us about the relationship between the two original vectors.
Right, that's the part I'm still trying to grasp. What does the scalar product actually tell us about the two vectors we're multiplying?
The scalar product is a way to measure how much two vectors agree in terms of their direction. Think of it like shining a light on one vector and seeing how much of its shadow falls on the other vector.
Okay, so the more those vectors align, the longer the shadow and the greater the scalar product.
Exactly. If the vectors are pointing in exactly the same direction, their shadows perfectly overlap, giving you the maximum possible scalar product.
And if the vectors are perpendicular, their shadows don't overlap at all, so the scalar product is zero. It's like they're not even acknowledging each other.
That's a great way to think about it. The scalar product captures that sense of agreement or alignment between two vectors.
Okay, that makes sense. And the textbook mentioned that the scalar product is commutative, meaning the order of the vectors doesn't matter.
That's right. You'll get the same result whether you do A dot B or B dot A. But now let's switch gears and talk about the vector product, the cross product. It's a bit more, shall we say, multidimensional.
Okay, I'm ready for the challenge. What does the vector product tell us that the scalar product doesn't?
The vector product, or cross product, gives us a new vector that's perpendicular to both of the original vectors. This new vector represents the area of the parallelogram formed by the two original vectors.
Hold on, a parallelogram? I thought we were talking about vectors, not geometry.
Vectors and geometry are deeply intertwined. If you draw two vectors tail to tail, they form two sides of a parallelogram. The vector product gives you a third vector that sticks out perpendicular to the plane of that parallelogram, and its length represents the area of that parallelogram.
So it's like a visual way of seeing how much space those two vectors enclose.
Precisely. Now, you might be wondering, how do we know which way this new vector points? Does it point up or down from the plane?
Yeah, that's what I was thinking. It could go either way, right?
That's where our trusty right-hand rule comes back into play. Remember, point your fingers in the direction of the first vector, curl them towards the second vector, and your sum will point in the direction of the vector product.
I'm getting better at that. So if I imagine those two vectors lying flat on a table, my thumb would point either upwards or downwards, showing me the direction of the vector product.
Exactly. It helps us visualize this 3D concept. Now, remember how we said the scalar product is commutative?
Right. The order didn't matter for the dot product. Is it the same for the vector product?
Nope. The vector product is anti-commutative, meaning that if you switch the order of the vectors, the direction of the resulting vector flips. So A cross B is not the same as B cross A. They have the same magnitude, but point in opposite directions.
Okay, so we need to pay close attention to the order of those vectors when we're doing a cross product.
Got it. And we saw how the scalar product is at its maximum for parallel vectors and 0 for perpendicular vectors. What about the vector product?
It's the opposite. The vector product is 0 for parallel vectors and reaches its maximum magnitude when the vectors are perpendicular. It's like a measure of their disagreement, so to speak.
Interesting. It seems like the scalar product and the vector product are kind of like two sides of the same coin, each providing a different perspective on the relationship between vectors.
That's a great way to think about it. They complement each other, giving us different tools to analyze how vectors interact. Now, to actually calculate these products, we don't need to draw parallelograms every time. That's where components come in handy.
Ah, those x and the y components are back to save the day.
Exactly. Instead of relying solely on geometric interpretations, we can use the components of the vectors to calculate both the scalar and vector products. It's a more systematic and efficient way to handle those calculations. So those components are really essential tools for working with vectors in a more analytical way. I'm excited to see how we can apply these concepts to real-world physics problems.
And we will. In the final part of our deep dive, we'll explore how these vector concepts played a crucial role in describing motion, forces, and other fundamental principles of physics. Stay tuned for the grand finale.
And we're back for the final part of our physics deep dive, ready to wrap things up.
Absolutely. Let's tie together all those fascinating threads we've been exploring.
We've journeyed through the nature of physical theories, the importance of models, the nuances of measurements, and those intriguing vectors.
We've built quite the toolkit for understanding the universe.
And speaking of tools, there's one more I remember from the textbook that we haven't talked about yet. Unit vectors.
Ah, yes. Those are essential for making vector calculations even smoother.
I remember there are those special vectors with a magnitude of 1 that point along the axis.
Exactly. They're like signposts in the world of vectors, showing us the way. We have I hat pointing along the x-axis, j hat along the axis, and if we're in 3 dimensions, k hat along the z-axis.
So it's like having a set of directions, making it easier to describe where a vector is pointing without having to use angles and trigonometry all the time.
Precisely. And the beauty of unit vectors is that any vector can be expressed as a combination of these unit vectors, each scaled by the corresponding component.
Right, so we can say something like 3i hat plus 4j hat to describe a vector that has a component of 3 in the x direction and 4 in the y direction.
Exactly. It's like giving the recipe for that vector, telling us how much of each ingredient the unit vectors we need to combine.
It's a much more intuitive way to work with vectors, especially when those calculations start to get more complex.
Absolutely. Unit vectors are a concise and powerful tool in the physicist's arsenal.
Well, I have to say, this deep dive has given me a whole new appreciation for the elegance and power of physics. Who knew units and vectors could be so fascinating?
It's all about understanding the fundamental building blocks of the universe and how they interact. And we've only scratched the surface.
You're right. There's always more to explore. This deep dive has definitely ignited my curiosity to learn more about the mysteries of the physical world.
That's what we hope for. It's all about fostering that sense of wonder and encouraging everyone to keep asking questions and seeking answers.
And on that note, I want to thank you, our expert, for guiding us through this incredible journey.
It's been a pleasure sharing these concepts with you and our listeners.
And to our listeners, thank you for joining us on this exploration of the fundamental principles of physics. We hope you've enjoyed delving into the world of models, measurements, and those intriguing vectors.
Remember, physics isn't just confined to textbooks and laboratories. It's all around us, shaping the world we live in. So stay curious, keep exploring, and never stop asking why.
Until next time, keep those physics brains buzzing,